Welcome to Praveen Patil, College of Diploma Engineering and Technology. So in this second part of video, we will be discussing to the remaining part, that is second part of the first chapter. So let's have a quick revision up till now what we have discussed. So in this first part of the chapter, we have discussed about the thermodynamics, what exactly thermodynamics in terms of simple statement. We have discussed about the four laws which are used in the thermodynamics: first law, zeroth law, second law, and the third law. We have also seen types of systems: open system and a closed system. This is the diagrammatic representation. We have discussed about the flow and non-flow process. Also we have seen some properties, that is intensive and extensive properties. And now today we will be move forward to the topic of zeroth law. So in this zeroth law, what does the zeroth law states is all about? Here three circles are given, named as circle 1, 2 and 3. So in these three circles, it says that suppose the temperature of the first circle is equal to the temperature of the second, then the third circle will have the same comparison temperature of these two circles. That means they will be having an equal in temperature to each other. That is about the zeroth law. So in the first law of thermodynamics, we will see the block diagram representation over here. Okay. So what does the first law of thermodynamics states all about is, no machine can produce energy without corresponding expenditures of energy. It's in terms of simple language, it is unless and until there is no spend of energy, there won't be any production of energy for the work purpose. It also states that, I am reading out this sentence, when a system undergoes a thermodynamic cycle, then the net heat supplied to a system from the surrounding is equal to the net work done by the system on its surroundings. So this is the formula: net heat supplied is equal to the net work done by the system. Now in the second law, this is the block diagram representation of Kelvin Planck statement. Now second law states that second law of thermodynamics has been applicable for the Clausius and Planck statement in slightly different word, although both statements are basically identical. Each statement is based on irreversible process. Now Clausius statement implies that it is impossible for a self-acting machine working in a cyclic process. Focus on this diagram. It is impossible for a self-acting machine working in a cyclic process unaided by an external agency to convey heat from a body at low temperatures. This is the low temperature, from a low temperature of a body to a high temperature. So in a simple terms, in a simple word, Clausius statement says that heat of itself cannot flow from a colder to a hot body. Heat of itself cannot flow from a colder to a hot body. Whereas Kelvin Planck statement, it states that it is impossible to construct an engine which will operate in a cyclic product. No other effort except to external heat from a single reservoir and do equivalent amount of work. See, this part is a work. This part is a work. Now we will be focusing this two statements in terms of this diagram, Kelvin Planck's diagram, block diagram representation. Now what does this block diagram states that, see this high temperature reservoir T1 and this low temperature reservoir T2. In between this there is a heat pump and a heat engine. Now usually what happens, in order to produce a work, heat is supplied, heat is required. So the heat from the lower temperature, that is Q2, is applied to the heat pump, and From that heat pump it goes to the high temperature. Now from that high temperature, that is Q1, it is applied. From that high temperature Q1 it is applied to this heat engine. So when a heat is applied to a heat engine, it will produce a work. So that work is calculated by taking minus of this Q1 and this Q2. I am erasing out this. So work is calculated by taking subtraction of this heat Q, that is Q1 minus Q2. So this is about Kelvin Planck statements. We will be seeing the Carnot theorem. Now what does the Carnot theorem states? Carnot theorem states that all the engine operated between a given constant temperature source and a given constant temperature sink, none has a higher efficiency than reversible engine. So this is a reversible engine. We will focus on this reversible engine later on. First we will discuss about Carnot. So over here in Carnot there is a source, as we are able to see source, and that is given as a T1. So it is operated between same source. This heat engine A and heat engine B is operated between the same source and a same sink. So the work done in heat engine A is being from the heat received from the source Q1A and goes back to Q2. So work done is said as WA. Okay, so work done is said as WA for heat engine A, whereas same thing is done for heat engine B, and the work done is represented by WB. Work done is represented by WB. So we will be seeing the efficiency, and we will be proving that this work done A is greater than work done B. So for this we will assume that efficiency of heat engine A should be greater than efficiency of heat engine B. So when we assume this, we have to take into consideration as this is operated between the same source and same sink. So Q1A and Q1B is taken as equal, that is Q1. So efficiency, the formula is represented as work done divided by heat supplied. So WA divided by Q1A, which is greater than WB divided by Q1B. Why greater? Because we have assumed that efficiency of heat engine A is greater than efficiency of heat engine B. Now as over here it has been stated that if it has been operated between same source, so the down value, that is Q1A and Q1B, will be taken as same and it will be removed. So we will be getting net work done of A is greater than net work of B. So this is all about Carnot theorem, and this violates the Kelvin Planck statement of the second law. Okay, so further this we will be focusing on reversible heat engine. Now in this reversible diagram, we will understand the diagram unless and until we will understand this first diagram. Okay, so when we understand the first part, we will be getting an idea of this, how the working of reversible engine take place. So this part is the source and this part is a sink, and this one is a reversible heat engine. I am zooming this. Okay, so when temperature from the first is applied to heat engine A, it produces a work WA. Now over here in a reversible heat engine B, work is applied, not heat, work is applied. So when work is applied to reversible heat engine B, it produces heat from sink Q2B to source, that is Q1A. Now here source T1 is taken as constant, that is it has been taken as similar. So we are drawing a line. So when we draw a line, the net work which is received is taken as subtraction of work done by heat engine A minus work done by heat engine B. So this altogether violates Kelvin Planck statement of reversed heat engine. Okay, so after this we will be looking for the efficiency of reversible heat engine. Now, efficiency of reversible heat engine. For this efficiency of reversible heat engine, efficiency of a reversible heat engine is taken into account by 1 minus Q2 by Q1. Okay, so for this I am utilizing just a minute. Now for this we will observe this part. We will be focusing on this part over here. Okay, now what happened is, here efficiency of heat engine is been taken into account, so it is been taken as 1 minus Q2 divided by Q1, this first part. So this Q2 and Q1 is represented, this Q2, this first part, this Q2 and Q1 is replaced by T2 and T1, and when we cross multiply this, we will get as T1 minus T2 divided by T1. So this is the efficiency. Now when we calculate coefficient of performance, this is the coefficient of performance. So for a refrigeration, I repeat, for a refrigeration, so this T2 and T1 is equivalent to Q2. So this is Q2 which I have written over here, and this is the value T1 minus T2 which is obtained from this T1. So when we rearrange this term, we will be getting 1 minus Q1 by Q2 minus 1. Okay, so this is of refrigerant, coefficient of performance for refrigeration. Now in order to calculate coefficient of performance for reversible, what happened is, over here for reversible, this Q1 and Q2 we take equivalent to T1 and T2. Now when we substitute this value over here in this, it will get T1 by T2 minus 1. Now this T1 by T2 minus 1 over here, we are doing reversible. So for reversible, the denominator value will go up and numerator value will go down. So we will be getting final value as T2 divided by T1 minus T2. So this is coefficient of performance for refrigeration in terms of reversible. Now same way for in terms of heat pump also we will be getting with the change in temperature, that is instead of T2 we will be writing as T1, and we will be getting coefficient of performance for heat pump as T1 divided by T1 minus T2. So till now we have discussed about the heat engine, reversible heat engine, and we have calculated coefficient of performance. So we will be, in the next part of the video, we will be looking for the boilers SFEF. We will be discussing about the applications in turbines. We will be discussing about the application in terms of throttling process, in terms of nozzles and condensers. So in the next part of the video we will be focusing on this. We will just have a quick revision what we have discussed. So we have discussed the Zeroth Law. Zeroth Law, what does it state? The temperature are indirectly equals with respect to the first, second and the third body. Now in the first law we have discussed how the net work done is equivalent to the net heat supplied. In the second law we have discussed about the Clausius statement and Kelvin Planck statement. We have seen in terms of block diagram representation with respect to the heat pump and a heat engine. Also we have seen the Carnot theorem, the work done of a heat engine A and the separate work done of a heat engine B. Also we have found out the work done of heat engine A is greater than heat engine work done by heat engine B. So this is how we have seen the equations. Also we have seen the reversible heat engine and we have discussed about the efficiency of reversible heat engine. Efficiency of reversible heat engine is also being calculated over here, and also the reversible heat engine, the efficiency is taken reciprocal of heat efficiency of engines. So that's all for today. We will be going for the next part of the video. Thank you.